Hello viewers and my dear students. Welcome to one-dimensional problems analysis. Now I'll be showing you a demo on one-dimensional bar analysis with two materials fixed at both the ends and with an axial load at the center subjected to thermal load. This is in fact problem 4. Previously in the problem 3, we had an axial load at the center but there was no thermal load. Now you have a temperature load also here. When temperature load is also there, how to overcome these problems in Ansys Mechanical APDL, I'll be showing it to you now. See here, this is the problem. See here, the bar is this way, okay, and this has a length of 200, this is aluminum, this has a length of 300, this is steel, and this is as usual, Young's modulus is 70E3, that is 70 into 10 to the power of 9 Newton per meter square, or 70E3 Newton per millimeter square. In the same way, it is 200 into 10 to the power of 9 Newton per meter square, or 200 E3 Newton per millimeter square. And the area of cross section is 900 millimeter square. Area of cross section of this is 1200 millimeter square of steel. And the important thing, when the temperature load is there, okay, the coefficient of linear expansion has to be there. This is 23 into 10 to the power of minus 6 per degree centigrade. This is 11.7 into 10 to the power of minus 6 per degree centigrade. Okay. Now as you see here, now initially there will be a temperature of 20 degrees. Then it will be, the temperature will then be raised to 60 degrees centigrade. That means the net difference in temperature will be 40 degrees. 40 degrees should be applied on both the materials. When more the temperature, that is the materials tend to become softer. As a result, there will be more and more deformations. That is why in this problem I am giving you one simple demo where both the material is subjected to a thermal load of 40 degrees centigrade, and you have an axial load also along with the thermal load, and what exactly will be the displacements. See here there will be at an axial load at the center here between these two materials, there will be a load of 3 lakh newtons is applied. Okay, and when there is a load in this way, the support at this support, this is positive x. In the negative x, there will be one reaction here, there will be one reaction here in the negative direction. The summation of these two should be equal to P only. That is cross verification what you should do once we complete the problem. Okay, this is the thing, and thus I'll show you how exactly to do. And I've told you 60 degrees to 20 degree means we have to apply a thermal load of 40 degrees also. And as usual, we have to find out nodal displacement, forces and stresses in each material, reaction forces and all that. We'll try to cover up using Ansys now. See here, I have already changed the job name, changed Gurudhar problem 4, and also I've changed the title also. Okay, I've changed the title also. As you see here, one-dimensional analysis with axial and thermal load. And if you see here, up till here, it has already been recorded, log file. Okay, up till here, two-dimensional analysis with axial and thermal load, already it has been recorded. Okay, see here, now we'll start with the problem. Preferences, structural, okay. Preprocessor, element type, add, edit, delete, add, link, as usual, link 180 only you take, okay you say, close you say, then real constant you do, add, edit, delete. First one is aluminum, as you know, it is, first one has a cross section of 900. 900 you put, okay, apply. Then second real constant 2 is 1200 you put. 1200 you put. Then say okay. That means there are two real constant, set 1 and set 2. Okay. And in the same way, you add material properties also. Material models, structural, linear, elastic, isotropic. Okay, Young's modulus for the first one is 70E3. Okay, be careful. It is 70E3 because they have given Newton per meter square. I have converted into Newton per millimeter square. It is 70E3. Okay, you say. And since the thermal load is given, compulsorily go to thermal expansion, secant coefficient, isotropic, and the thing is, it is 23E minus 6, 23 into 10 to the power of minus 6 per degree centigrade. This is the coefficient of linear expansion. That also you put. Then I put, this is material property. This is coefficient of linear expansion. Both are put. Then material, new model. Okay. Take this. Okay. Elastic, isotropic. The second material, as you know, it is steel. 200 E3 or 2E5. Okay. This you do. Then coefficient of linear thermal expansion, secant coefficient, isotropic you do, and you put 11.7 e to the power of minus 6. 11.7 e to the power of minus 6 also you put. Okay. Then you say okay. Then you have two materials with that is a linear quotient of linear expansion added and all that. Now you material exit. Okay, then you start doing the modeling. Modeling, create key points in active coordinate system. This is material 1, that is key point 1 is 0, 0, 0, 0, 0, 0 you put. Then say apply. Then key point 2, okay, key point 2, as you know it is 200, 0, 0. Key point 3 is 500, 0, 0. 500, 0, 0, okay. Okay, as you see, it is all from this problem. I'm just giving you, it is key point 1 is 0, 0, 0, 200, then 500, 0, 0. Key point 1 is 0, 0, 0, key point 2 is 200, 0, 0, key point 3 is 500, 0, 0, 0. In that way, you understand how exactly it has to be done. Okay, this I've done. Now I'll create lines, straight lines. I'll join 1 to 2, 2 to 3 I'll join. Okay, I just joined. Okay, now you see here, the important thing is meshing. Meshing, under meshing, no, this you have to make Ansys know that this is aluminum and this is steel. That is, this aluminum has real constant 1, real constant 1 and material 1. This has real constant 2, material 2. Okay, in that way, when I go meshing, mesh attributes, picked lines, you click on the first line and say it is 1 and 1. 1 and 1 you take it, okay. Then say apply. Then take this and say 2 and 2. This is 2. This is 2 you say. Okay, now we have clearly assigned. Now Ansys knows that this is aluminum and this is steel and we have fed the proper real constants and all that. Okay. Now once you do that, you go for size controls, manual size, lines, picked lines, this and this you take, say okay, and number of divisions give only 1 because too many elements don't give. It is 1 is enough for this. Just say 1. Okay, once you do 1 and 1, then you are creating only 2 elements. Then mesh, lines, pick all you do. That means 2 elements have been created here. If you go for list, elements, attributes and real constant, you see there are only 2 elements created, 1 and 2. 1 has a real constant of 900, 2 has a real constant of 1200, both are okay. Okay, in the same way, if you go for list material properties also, all materials, you see here clearly first material is aluminum 70,000 or 73 and next is 2E5, that is also correct, and this 0.23, that is 23 into e to the power of minus 6, this is 11.7 e to the power of minus 6 or 0.117 into 10 to the power of minus 4. The properties and all that we have fit properly. Okay, now we are going in the correct direction. Okay, this is up till here. You can save at this. Okay, in case you make a mistake later on also, you just say resume DB. We'll come back to this. Now we have come to pre-processing stage is over. Now we go to the solution phase where we load this. Loads, define loads, apply, structural, displacements, on key points you take, here and here, you fix at both ends. That is all degrees of freedom, you make it 0. Okay, you fix at both ends. Now force moment on key points. Okay, force moment on key points, you click here. There you have a load of Fx 3 E5. Okay, that means 3 lakh newtons is applied there. 3 into 10 to the power of 5 newtons is applied at that. Okay, this is an axial load. You see here, axial load. Other than that, you have a temperature load also. Temperature load 20 degree to 60 degree means the difference is 40. 40 should be applied on both the lines. Temperature on lines you take, click on this line also and say OK, and temperature you take it as 40. Okay, then once you do this, okay, then we can go for the solution. You can solve this, and current LS also you do. Okay, once you do this, the solution is done, message should come. It takes some time. Okay, now it has come. Now we are doing in the that means we have adopted the correct procedure and there are no mistakes till now. In that way, just say close. Okay, see here, once you have got this, see carefully, this is the solution phase is over. Now general post-processing. We have gone to the third phase where we are extracting the results. Okay, the important thing I told you, list results, reaction solution you do first. Reaction solutions, all items if you do, it is 3 lakhs, no? See here, be careful. I have applied 3 lakhs here, okay? And because this is positive X, this is negative X, this is also negative X. It is supported here, it is supported here. Reaction will be supported at this support and reaction will be supported at this support. Reaction will be developed at this support, reaction will be developed at this support. Then, as you see, at node 1, there is a reaction of minus 11,436 and the reaction at node 3 is 0.28856 into 10 to the power of 6. If you add these two, okay, this is 2,88,000, this is 11,436. In that way, if you add up these two, you should get 3 lakh newtons only. That means this is a correct answer what we have got. In that way, this has to be recorded. This you make a tabular column, node 1 and node 3 only, because the reactions will be developed only at the that is supports. This you record it. This you have to make a tabular column. Okay, in the same way, nodal solution you go. Okay, DOF solution, displacement vector sum you give. In that way, if you see here, this is node 1 and node 3. You don't get any, because it is all fixed. There won't be any displacement. At node 2, 0.22030 is the thing what you got. That is perfect. This is the displacement at node 2 in the positive X direction. That is also correct. This also you record it, make a tabular column in your record and all that. Okay. This is also a very important result. Then you go for element table, define table, okay, add, then by sequence number, SMISC 1 you go for member force, apply, then by sequence number, LS 1 also you give for axial stress. Okay, SMISC 1 and LS 1 you give, then just say close. Then what you do is list results, element table data, SMISC 1, LS 1 you take and just say this is perfect way. You see here, first one, member force, that is in the aluminum, you have tensile stress and tensile force and tensile stress. In the second one, negative, no, it is compressive force and compressive stress. Okay, perfectly it is. This also has to be done correctly. This also has to be recorded. Now what you see here, the important thing here is in the list log file, no, list log file, okay, you copy the entire thing here. Control C, okay, if you copy the entire thing, okay, and if you paste it here and enter, you are getting the entire results back. Okay, if you here and copy the entire thing and say Control V, you are getting the entire thing back. Okay, that means the solution can be done in that way also. Okay, this is the end of this problem. Thank you friends, thank you for watching. Thank you.